All right, in this video, I'm going to go through the review for the exponential expressions and equations unit. So for this first one, I want to graph f of x, which is 1/2 to the negative x minus 6, which is some sort of exponential decay function that has two transformations attached to it, right? That minus x and then figuring out what that minus 6 does. So from a conceptual standpoint, I start by thinking about what the original parent function would look like. And I know that when I plug in 0 for x, I would get out 1 as a y-intercept, right? Because anything to the 0 power is 1, and it's a decay function. So it probably looks something like this, where it curves off towards 0. Oh, I can do a little bit better. But it never intersects 0, because this does happen to have a horizontal asymptote of y equals 0. Imagine, right? I can plug in bigger and bigger values of x there, and I would just get 1 over some big number, which is going to trail off towards 0, but not quite 0. So the question is, what do those two transformations I've highlighted do? Well, the negative x is going to reflect this over the y-axis. So after I perform that transformation, it could look, and I'm just doing a rough sketch for now, I'll get some actual points in a minute, could look something like that. But then keep in mind that if I subtract 6 from a function, I'm essentially translating that function down 6 units. I'm taking all of the y values, all of the outputs, and minusing 6 from them. So it's probably going to look something like this when I go to graph it. So if I keep track of my y-intercept there, if I translate that 6 units down, I think that would end up being, let's see, 1, 2, 3, 4, at 0, -5, right? Because that's 6 units down from 0, 1. So if I look to see where my original horizontal asymptote was at y equals 0, if I translate that 6 units down, I think that would now be at a y value of 6. Right, so maybe something like right there. And I want you to convince yourself that that's true just from an algebraic standpoint. I'm going to erase all this thought process work now. Convince yourself that this is going to trail off towards 6 in some direction, right? Of that, if I look at this function, for very large values of x, as x gets larger and larger and larger, this actually gets bigger and bigger and bigger, because that's the same thing as 1 over negative x divided by 2 to the negative x, or equivalently 2 to the positive x over 1 to the positive x, which of course would just be 2 to the x. So off to the right, for very large values of x, that's going to get bigger and bigger and bigger, right? 2 to a big number is a huge number. But as I plug in smaller and smaller x values, as I go to the left, I want you to keep in mind what would happen there, right? Like, let's say I plug in a big negative number. Well, since my exponent's already negative, that would just be some big positive number when I multiply it by a negative. So I run into the same issue where this part of my function is getting closer and closer to 0, and then I'm subtracting 6 from it, which would mean all of my outputs to the left-hand side are, in fact, approaching y equals -6. So let's try to sketch this now. I'm still missing one important part here. Obviously, if I had, a set of axes and a grid here, I would want to get a lot of points. But I do know that off to the left, it's going to curve towards -6. And off to the right, I'm going to move my label for the y-intercept there so I can graph that. It should curve up, and then eventually, like we had discussed, shoot towards infinity. The question is, where does that intersect the x-axis? Because the question you'd have to ask yourself algebraically is, when is the output equal to 0? Or if I add 6 to the other side, what value of x would make 1/2 to the negative x equal to 6? And the problem is, I don't think there's any integer value that will work there. I can't think of a way to get 6 to have a base of 2 or a base of 1/2. So this is an instance where I would be forced to use my calculator based on the algebraic skills we have at the moment. So I'm going to take out my TI-84, and let's see what happens there. Right? This is my function. So I'm going to graph that in y equals just to see what it looks like. Right, I want to confirm that I'm graphing this correctly. And if you want to get a fraction, I like to use alpha y equals, but depending on how updated your calculator is, you could do alpha x. That'll work as well. Keep in mind that when you type in negative x for the exponent, you should be using the negative button next to the decimal point, not the subtraction sign. But when I subtract 6, that's when I would want to use the subtraction sign. And if I graph this, this does look pretty much like what I thought it was going to look like. And it looks like my x-intercept is a little bit before 3, perhaps. So how do I get that? Well, if I hit second trace, I have a lot of functions here. I could find what a minimum value is, what a maximum value is, what an intersection between two curves is, but I'm looking for the x-intercept. So I'm looking for when is the value of this function 0. So I'm going to hit enter there. Then my calculator is going to ask me for a left bound. So what I'm going to do, mine's a little slow, yours should probably work a little bit quicker than this, is I'm going to arrow over until I'm a little bit to the left of where I think that 0 is. And I'm going to hit enter there. And then it's going to ask me for a right bound. So I'm going to arrow a little bit over to the right and hit enter. And essentially what that's doing is that's giving your calculator a range of x values to look through to see where your function's equal to 0. In case there might be multiple zeros for a function, you need to specify which one you're looking at. So now it says guess. So if I hit enter one more time, it actually does calculate that for me. I don't know if those are all the decimal places. So for now, I'm going to round that to, let's say, I don't know, 10/100th. Let's round it to the 1,000th for now. On the test, it'll be specific. And then I think that has enough to at least give the shape of this curve, where, of course, if I'm graphing this and I needed to get more specific points, I can go to second graph to get a table of values and then plot as many values as I can, scaling my axes nicely. All right, so that's for a graph. I'll leave number 2 for you to try on your own. We also did a lot with simplifying exponential expressions using our rules of exponents. So let's start with A here. A lot going on, but I noticed that everything in these parentheses are being raised to the 4/3. So eventually I have to deal with that. But before I do anything, I'm actually going to rewrite that x to the 4th under a cube root. I know by properties of rational exponents, that's the same thing as x to the 4/3. And that might be easier to manipulate algebraically if we have that. Now, you got two options here. One of them is to multiply all of your exponents in the top and in the bottom by 4/3. Or you could try to simplify what's in the parentheses first and then deal with that outside exponent. It doesn't matter which one you choose to do. In this case, because there's so much going on inside the parentheses, I'm going to try to clean that up first. So my first thing I notice is that 3 of my expressions, this one, and it's a little bit hard to see, but this one as well also has a negative exponent, that y to the negative 4/3. All of those have negative exponents. So I'm going to swap where those are so I can make those positive exponents. So my y to the negative 4/3 is going to the numerator, so that I can make that y to the positive 4/3. My x to the negative 3/2 is going to go to the denominator, so I can make that x to the positive 3/2. And my y to the negative 1st is going to go in the denominator, and I'm going to make that y to the positive 1st as well. Now I'm putting it over there because I want to actually put all of my x terms next to each other so that I can look to see which exponents I'm going to add to each other. So I've got that cube root of x to the 4th, or again, I could write that as x to the 4/3. And I have an x to the 5/3 as well down there. And again, this is all being raised to the power of 4/3. Now I could clean this up a little bit still on the inside. Keep in mind if I'm multiplying like bases, I can simply add those exponents. Now you could get a common denominator, or since you have a calculator, you could add all those in your calculator. And I do believe you should end up with x to the 9 halves if I add 3 halves, 4 thirds, and 5 thirds. And similarly, I notice I am dividing y to the 4 thirds by y to the first. So I can subtract those exponents. That one you could probably do in your head, right? 4 thirds minus 1, or 3 thirds, should be y to the 1 third. And still, I need to keep in mind, I'm raising all of this to the 4 thirds. Right, so my last step here would be to apply that 4 thirds to both my numerator and my denominator. Right? When I'm raising something that has an exponent to another exponent, I can simply multiply those exponents. So 1 third times 4 thirds would be 4 ninths, right? Multiply the numerators and multiply the denominators. And when I multiply 9 halves times 4 thirds, try to do that in your head a little bit, see if anything reduces, because this one actually works pretty nice in that if I cross simplify here, 2 divided by 2 is 1, 4 divided by 2 is 2, and then 9 is divisible by 3, right? 3 goes into 9 3 times, and then I would just be left with 3 times 2 divided by 1 times 1, which would just be 6. So my fully simplified expression would look something like this. It's kind of hard to check if you did this correctly, but what you could do if you had an ample amount of time is you could pick a value for x, pick a value for y, substitute in, and then pick a value for y, pick a value for x, substitute in there, and make sure you get the same output in your calculator for both those. Again, I'd only recommend that if you have time. That tends to be a pretty tedious process for stuff that looks this ugly. So let's try one more. For b, same sort of deal, but now we have a coefficient to worry about as well. This set of parentheses is telling me that that negative 2 exponent applies to this coefficient of 2 as well. So since there's not a lot in the parentheses there, I think this exponent is where I'm going to stop. So I'm going to rewrite just my denominator for now. I'll deal with that in a minute. But in my numerator, I'm going to have 2 to the negative second times x to the negative 2 thirds times negative 2 would be positive 4 thirds. And then negative 4 thirds times negative 2 would be positive 8 thirds. So now I could start subtracting exponents since I'm dividing, but again, since I have negative exponents, I'm just going to swap where they are real quick, especially for that 2 to the negative second. I want to make sure I deal with him. Right? This term and this term should swap places so that I can make them positive exponents to make them easier to operate on. So I'm going to rewrite this as 6 times x to the 4 thirds times x to the 7 thirds times y to the 8 thirds divided by 2 to the second times y to the 1 third. And now this is pretty easy to clean up from here. I've got 2 bases of x being multiplied, so I could add those exponents. Problem is, I think I rewrote that as 7 thirds. That should be what, 7 fourths? So that's going to make life a little bit harder, given that I have to add those and they don't have a common denominator. But again, you can get a common denominator, or you could add those in your calculator. It should be 37 twelfths, what that adds to. And then if I do y to the 8 thirds divided by y to the 1 third, those do have a common denominator. So if I subtract those, 8 thirds minus 1 third is 7 thirds. And then 2 squared is all I have left with there, so that's just 4. Now, this is almost simplified completely. A lot of the times, once you move all of your numbers around, the ratio of your constants might reduce a little bit further, where in this case, I have 6 over 4, which I know reduces to 3 halves. So I can write this as 3 times x to the 37 over 12, y to the 7 thirds, divided by 2. Or, equivalently, if I wanted to put that 3 halves out in front, I could do that as well. But both of these are equivalent, so it doesn't really matter which one of these you use. They both represent a fully simplified form of our original expression after we apply all of our exponent rules. So that's if I strictly just have a bunch of exponents. But what if I have some radical expressions and I'm trying to express some things in simplest radical form? Well, my goal would be to reduce any of the radicals I have and then see if I can combine any term with like radicals. So for this first one, I see a 3x cubed under a square root. Well, I know 3 can't break down at all, but x cubed, I think to myself, can be broken up into radical x squared times radical x to the first. And the reason I'm doing that is because x squared is in fact a perfect square because it has an even exponent. The square root of x squared, provided we have a positive value of x here, so we're going to make some assumptions and assume that x is strictly greater than 0. That would simplify to x. So essentially my first term could be 5x times the square root of 3x. And if I try that same trick for my next expression, I have a 27, so a little bit larger number. But I can think of a perfect square that divides into that, right? 9 would divide into 27 3 times. And for x cubed, I could do the same thing where I break it into x squared times x. So both of these expressions are perfect squares under a radical, so I could simplify those, right? The square root of 9 is 3, and then when I multiply that with the 2 out in front, that would just turn into a minus 6. And again, the square root of x squared is just x, so I could pull that out, and all I'd have left with under a radical is the square root of 3x, which is good, because these actually are like terms. They both have the same exact radical expression, same index, same radicand, or thing under the radical, and they also have the same variable to the same exponent. So if I just wanted to combine these coefficients, in simplest form, I can make this -1 radical x, or -1x times radical 3x. That's not to say that they'll always simplify super nicely. 9 times out of 10 they will, but you could run into instances where they don't, and you're going to have an issue. So let's take a look at number 6, where now instead of a square root, I need to be thinking about a cube root, which is a little bit different because now when I look at 625, I don't ask myself what's the biggest perfect square that divides into it. I ask myself what's the biggest perfect cube. And remind yourself, sometimes I like to write them down. The perfect cubes are like 8, right? That's 2 cubed. 27 is 3 cubed. 4 cubed is 64. 5 cubed is 125, etc., etc., right? The numbers get pretty big pretty fast, so you probably don't need to write down too many of them. Okay, for the cube root of 625, as I'm consulting my list, I think there's only one obvious answer for what could potentially divide into that. I think that's 125, right? So this, you could write them in separate radicals if you want. You don't necessarily have to. But just to show you where I'm getting these numbers from, I think of 625 in my head as the cube root of 125 times the cube root of 5. So that cube root of 125 is just 5. So I will have a 5 on the outside, but in my cube root, I will also have a 5 somewhere hanging out. And then when I look at that y to the 5th, I think to myself, well, what could I break that into where it would be a perfect cube times something that isn't a perfect cube? And for a perfect cube for a variable, my only constraint is that I would need the exponent to be divisible by 3. So I think I could break that into y cubed times y squared, right? Because the cube root of y cubed is y, and y squared doesn't break down anymore, so I will leave that under the cube root. Make sure that in each step of your work, you are writing those down as cube roots, right? I know you're used to writing square roots, but this means something a little bit different here. Okay, so that's for the first expression. We've simplified that. I'm going to erase that just so I have some room to work. Let's see what I could do here. There's nothing I could do with the 5, but the cube root of y cubed is just y. So I could pull that out on the outside, multiply that to the y I already have, and make that plus y squared times the cube root of 5. These are not like terms. They don't have the same radicand, right, the same thing under the cube root. They don't have the same variable to the same exponent. So my hope is that when I simplify this third expression here, that it will look something like this or something like this, so at least one pair of them will combine. So let's see what happens. For -40, I think I'm going to make that the cube root of -8 times the cube root of 5. And now it's okay to have a negative under the cube root, right? Because if I multiply a negative to itself 3 times, the output would still be negative. So if I do that, this would be -2, and then times the y I already have out in front would be minus 2y. And then under the cube root, I still have that 5, and I still have the y squared. So there's 3 separate terms here. This one, and this one. And I'm looking for things in common. And I notice my first and my last ones both have the same radical. They both have the variable of y raised to the first power on the outside. So I can just combine those coefficients and do 5y minus 2y to get positive 3y times the cube root of 5y squared. And there's nothing I can do to simplify that, so I'm just going to write that as plus y squared times the cube root of 5. Sometimes you will be able to combine all your terms, sometimes you won't. You need to be very meticulous as you're going through simplifying these radical expressions. So that's if I'm adding or subtracting radicals. For multiplying and dividing, it works in a similar way, but there are some shortcuts that you could take. Like if I'm dividing 2 of the same radicals, right? This is a square root divided by a square root. I can equivalently interpret that as this. Because then I would be able to maybe simplify the 108 divided by 6, the x to the 5th divided by x, and simplify from there. Otherwise, you'd have to do this in 2 steps. You'd have to simplify the numerator, you'd have to simplify the denominator, and then divide. I'm trying to work smarter, not harder, because when I just write these under the same radical, I get 18x to the 4th y cubed, which is much easier to look at and much easier to simplify. Right, again, I'm thinking about a square root now. So 18 I could break into radical 9 times radical 2. X to the 4th, there's nothing I need to do with because that is already a perfect square because that exponent is even. But for y cubed, that exponent is not even, so I'll break that into y squared times y. And just as a side note, if that was a higher power of y, if that was like y to the 11th, when you're breaking that down, you want to make sure you pick the largest even number that you could break that up into. Because the whole idea of simplest radical form is that you're trying to get the thing under the radical to be as simple as possible, so the smallest exponent that you can get. Anyway, as I'm simplifying this, radical 9 is 3, radical x to the 4th is x squared, and radical y squared is just y. Again, we're assuming that these are positive values. We're assuming that nothing interesting has happened, that we don't have a negative input where I'd have to worry about the absolute value of x or something. So this is just working with those algebraic rules from there. All right, for this next one, we've got a couple of options of how to attack it. I could try to simplify these things in the numerator first, and then divide it by whatever's in the denominator. But again, I don't want to simplify more radicals than I have to, so the first thing I'm going to do here is I'm going to rewrite this a little bit to make it a little bit more obvious how I might want to simplify this, right? I'm dividing 2 terms by 1 term. Try to think about what we do with the quadratic formula when we're at the end of it, right? It's always okay to separate when you're dividing by just a single term here. So in this case, I could divide the outsides. So for the first one, 12 divided by 4, easy, 3. And then for those 2 radicals, again, if I write them under the same radical, 40 divided by 5 is 8a to the 4th divided by a is just a cubed. Similarly, I could end up with 2 times the square root of 3a squared. And then I try to simplify from there. You always have to ask yourself, am I looking at a cube root? Am I looking at a square root? Am I potentially looking at a 4th root? Because that determines how you break down those constants and those variables. But in this case, 8's pretty small. So 4 can go into that. And a cubed, again, pretty small. That's just a squared times a. So 3 times 2 would be 6, times radical a squared turns into a. And what I have left with under the radical is 2a. For this radical over here, not much I could do other than that a squared, which I know the square root of a squared is just a. And these do not have like radicals, so there's nothing I could do there. I guess you could factor out a 2a from both of those, but you don't necessarily need to. So something like that could be simplest form. Now, for number 10 here, we also did exponential regressions this unit. So the first part of this, asked, using the data in the table, create a scatter plot on the grid below. I've already taken the time to do that. Notice I have not connected these points because I don't have any data values in between these numbers, right? I know normally we connect 0 to 1, but if I were to do that here, that would imply that I have data for all the values between 0 and 1, which I very much do not. Just keep in mind with how we've defined this, our inputs for time represent the number of years since 1984, and our output represents an average salary of a baseball player in thousands of dollars. So it's not like they're making $290, they're making 290 thousands of dollars. So it's scaled like this to make the numbers a little bit smaller to work with. So I already made the scatter plot because I wanted to look at the data and see what sort of trend this looked like. And to me, this looks like it could be modeled pretty nicely by an exponential curve, right? So what I'm going to do is I'm going to get the exponential regression equation for this with my numbers rounded to the nearest hundredth. So I'll remind you of how to do that in your calculator. If I take out my handy dandy TI-84, right, and if I hit the stat button, which is right below delete, and if I hit enter on edit, I'll have a place where I could type in a list of values. L1 stands for list 2, L2, or L1 stands for list 1, L2 for list 2, and so on and so forth. So I've already done this ahead of time. What I did is I typed in all of my inputs that I have along the x-axis for my L1s, and I typed in all of my outputs for L2. Once you've done that, do me a favor, just go through and check them. Make sure, let me put this here. Make sure that, you know, all of your values are there. You don't want to be missing anything. Because sometimes if you've missed one, you won't know because you don't have any context for what these numbers should look like in your equation. Once you have those, if you go back to stat, again, right under delete, arrow over to calc, you'll notice you have a lot of different types of regressions you could do. You could do a linear regression, quadratic regression, cubic, and the one for 0 says exponential regression. If you hit enter on that, you'll notice that your X list is already populated as L1, the Y list is L2. So all you have to do is, depending on your calculator, you could hit enter a bunch of times, go down to calculate, and it should crunch those numbers for you. So if I wanted to write an exponential regression equation of this form, you know, it tells me this is my A value, and it tells me this is my B value. We'll talk about what those mean in a minute, because context-wise, they do make sense here. And they want me to round them to the nearest hundredth. So I'll do y equals 276.67 times 1.21 to the x. They didn't ask me to name this anything in particular, so I don't need to do anything fancy with this. But keep in mind, you know, if I asked you to name this f of t or something, then you would need to have the output variable as f of t, and you need to have your input variable as the exponent as t. So depending on the instructions, that might change, so be careful of any notation issues that might arise. But I want you to look at our scatter plot here and, you know, convince yourself that this would make sense based on what the scatter plot looks like. This would be the starting value for whatever our exponential function would be of best fit, and you know, it's somewhere between 300 and 200, so that fits. And this 121 means that we would grow at a rate of 21% every year, which would cause it to increase over time, not decay. So I think that fits with what we have here. Now, if I wanted to use this regression equation, there's a couple things we could do with that. I want to estimate the salary of a baseball player in the year 2005 to the nearest $1,000. So I need to be careful here. I remember that my inputs are defined as the number of years since 1984. So an x value of 0 actually corresponds to 1984. So if I need to figure out what x value would correspond to 2005, well, I could subtract those years and just see what I get. Right? 2005 divided by 19, subtracted by 1984 would be just, 21 years since then. So that's what I'm going to use as an input. So I'm going to take my exponential regression equation, and I'm going to substitute in 21 as an input. So as an output, if I round this, I get about 15,151 thousands of dollars, right? Because that's what our outputs are defined as. So even though they asked me to round to the nearest $1,000, it's technically asking me to round to the nearest integer that I get from my output here, because my outputs are already measured in thousands of dollars. So conceptually, these are not hard problems to do. But it's very easy to lose a point somewhere by worrying about, like I had said, a notation issue or some sort of rounding issue. So please be very careful as you're going through that. Now for solving some equations with rational exponents. All right, so the general structure for solving an equation with a rational exponent is to isolate the expression being raised to that rational exponent, then raise both sides to the reciprocal power and go from there. So I'll start by dividing out that 8 because that exponent of 2/3 does not apply to that. That 8 is simply linked by multiplication. So if I do that, I get 25 on the right-hand side, and on the left-hand side, I still have that 3x minus 1 to the 2/3. So if I want to undo an exponent of 2/3, I would raise both sides to the 3/2 power. So like do this, 3/2, 3/2. And the reason that works is because when I raise something to an exponent to another exponent, I would just multiply those. And 2/3 times 3/2 is just 1. So that would leave me with 3x minus 1 on the left-hand side. Almost. You know, the thing is here, on this side, it doesn't look like it, but if I think about what that rational exponent means, that means take a square root and then, you know, raise that to the 3rd power, or in either order, right? So what happens here is that I'm doing that same thing of I'm taking a square root and I'm raising it to the 3rd power. I'm doing both those things. So if I raise it to the 3rd power first, watch what happens. And you don't have to do both these steps. I just want to show you conceptually why this occurs. And I'm going to raise both sides to the 3rd power. I'll leave this as 25 cubed just for now. But I end up with 3x minus 1 squared. Okay, well, this is just a quadratic, right? You've seen this so many times throughout your life in Algebra 1 and Algebra 2. And to undo a squaring of something, I take a square root. But keep in mind that a square root function gives positive outputs only. So technically, this left-hand side should be the absolute value of 3x minus 1. Those are the absolute value bars. I know the 1 makes it look a little weird. It's a 1 there. Oh, I don't think that made it better. And that equals the square root of 25 cubed. I'm writing it like this because it'll be easier for me to evaluate in my head, because I don't know what 25 cubed is, but I certainly know what the square root of 25 is. And this equation would yield 2 solutions. One where the output is positive and one where the output is negative. So generally, as a rule of thumb, if you are taking an even indexed root at some point, which we're taking a square root here, to fix that, I can just make that 3x minus 1 as long as I set it equal to the positive and negative of whatever that output would be. Now, and if I did that real quick in my head, the square root of 25 is 5, and 5 cubed is 125. So now I have my 2 equations that I could branch off into. But the reason that happens is because that technically should have an absolute value bar on the left-hand side. We're dropping that just to make the algebra a little bit simpler. So it could be the case that 3x minus 1 is equal to positive 125, or I'll have a solution when 3x minus 1 equals negative 125. And if I solve both those, I'll get, if I add the 1 and divide the 3, I get x equals 42. Or if I add the 1 and divide the 3, I get x equals negative 124 over 3. So this equation actually has two unique solutions because we ended up taking a square root. That'll happen anytime you take a square root, a fourth root, a sixth root, any even index of a root that could happen. If you're unsure of that, whether there should be one or two solutions, what you could always do is you can graph this left-hand side in your calculator, put it in y1, graph the right-hand side, put it in y2, and you'll notice that those two functions intersect at 2 points. They intersect at an x value of 42 and an x value of negative 124 over 3. So you always have backdoors to check yourself through, provided you have a calculator. Now, for something like b, we're actually not going to run into that issue. So this is actually a much easier problem to solve, because if I add that 1 over, and if I raise both sides to the reciprocal power, I'm raising both sides to the 2/3. And I do not run into that same issue that I had, because when I'm raising something to the 2/3, I'm simultaneously squaring it and taking a cube root. Totally fine to take a cube root. I'm not going to run into an issue there, because a cube root function could have positive outputs or it could have negative outputs, right? If I multiply a negative number to itself 3 times, I get a negative number. So that's not going to cause any issues here. So I could just cancel those exponents and solve it the same way I normally would. Now this is a quadratic, so my goal is to still get one side equal to 0, factor it, and then take advantage of that zero product property, right? If I factor x squared minus 3x plus 2, those numbers are small enough to work with, right? Factors of positive 2 that add to negative 3. So my two solutions are 2 and 1. And if you're ever unsure of if those are your solutions, they should satisfy the original equation. So especially since you have a calculator, should be pretty quick to plug back in. All right, so let's try one more equation just to see what happens. All right, so I'm going to add the 20 over. So I have 5x to the 4/5 equals 1280. And then again, that 4/5 exponent does not apply to a 5. I don't see a set of parentheses there. So I'm allowed to divide the 5 out. And as a matter of fact, that's the easiest way to do it. Otherwise, I'd have to raise that to the 5/4 to get x to the 4/5 equals 256. So now I'm going to raise both sides to the reciprocal power, raise this to the 5/4, and raise this to the 5/4. And this is the most common mistake I see. I want you to be thinking about what this rational exponent means. It means to raise both sides to the 5th power and also take a 4th root. So when I'm taking a 4th root, that's an even indexed root. Imagine doing that in 2 steps, right? If I raise both sides to the 5th, those 5s would cancel, and I have x to the 4th equals 256 to the 5th. Again, I'm not going to evaluate that right now because that's a huge number. Leave that as is. But then I would take a 4th root. And the 4th root of x to the 4th is not x. It is the absolute value of x, which would mean the absolute value of x is equal to the 4th root of 256 to the 5th. Or in other words, that x is equal to, and then if you don't know what the 4th root of 256 is, you can check your calculator for that. And then you could raise it to the 5th power, because you actually do get a pretty nice integer out of this, where x is equal to the positive version of whatever that reduces to, and the negative version of whatever that reduces to. You do not need to show this step in your work. I just need you to understand why I'm using the positive and the negative versions here, because this is an even indexed root that causes that issue. If I'm having an odd indexed root, an odd number in the denominator, I'm not going to run into that issue. So you could see one example of each, you could see only one of them, but you need to be thinking on your toes when you see an equation with rational exponents. All right. Let's consider, for number 12, the following inequality where n is a real number. 1 over n raised to the negative second is less than 1 over n squared. And I want to know for what values of n will that inequality be true. I don't know about you, but I sometimes have trouble thinking about negative exponents, so I'm going to rewrite that left-hand side a little bit differently, right? That's 1 to the negative second over n to the negative second. And the right-hand side is just 1 squared over n squared. But if I rewrite that left-hand side, I could just make that n squared over 1 squared, or just n squared. So really, an easier way to think about this inequality would be what n values could make n squared less than 1 over n squared. Now, I don't know what n could be, but I certainly know that n should be a positive number, or a negative number, or 0. But I can rule that out right off the bat, because I don't think either of these original expressions would be defined if n was equal to 0. So now, if you're unsure, the easiest thing to do would be to guess and check. Let me pick an n value of 5, just to see what happens. And I'm hoping I notice something when I do this. Okay, so let's see, 5 squared. And you might already see where this is going. Is that less than 1 over 5 squared? And the answer is absolutely not. Of course not. Because I do notice that that right-hand side, if I pick an integer value of n that's greater than 1, this right-hand side is always going to be less than 1, and that side is always going to be greater than 1. So I can't pick a number that's greater than 1. So let me pick a number that's less than 1, something like, I don't know, maybe 1/2, just to see what would happen. And then I notice something magical happens here. And this is not the only way to analyze this. There's many ways to do this. I'm just showing you the number sense for why this works, right? I'm checking to see if 1/2 squared is less than 1 over 1/2 squared, where that would be 1/4, and this is 1 over 1/4, which would just be 4. And that does check out. 1/4 is in fact less than 4. So I think we found at least one number that works. And we found at least one number that doesn't work, right? N cannot equal 5. So the question is, what's the difference between these? This number right here is between 0 and 1. So any n value between 0 and 1 should work, given that it will cause this left-hand side to be some number less than 1, and the right-hand side to be some number greater than 1. You can test that out with any of those rational numbers between 0 and 1. Right? The whole idea of why that works is because I'm dividing 1 by something that is now less than 1, which will cause this entire right-hand side to be greater than 1. But you need to be careful, because that's not the only interval that works. Given that I am squaring n here, I would get all of the same conclusions for this interval right here, if n was between -1 and 0. Because if I were to plug in, let's say -1/2, I'm going to amend what we have right here, negative, we end up at the same conclusion, where a negative squared is positive, and 1 divided by positive 1/4 still would still be positive 4. Right? The idea is it forces the left-hand side to be less than 1 still, and the right-hand side to be greater than 1. Now, that's with me analyzing this with respect to just using exponent rules and leaving this as a rational expression. You could have done this in a much easier way if you simply looked at this inequality and multiplied both sides by n squared, so that I instead interpret this inequality as n to the 4th is less than 1, and then that's much easier to think about. I would need to ask myself, what n values could I raise to the 4th to ensure that I get it less than 1? But there's a reason why I didn't write it like that. Because if I write it like this, you might forget about the fact that n can't be 0. So you might end up at this interval right here, which is very wrong, given that n cannot be 0. There is a specific value within that interval that cannot work here. So just try to be careful as you're going through these sort of analytical exponent rule questions. Okay, so for the last one here, I want to algebraically verify the following identity for integer values of x using the properties of exponents. So essentially, I want to get either the left-hand side to look like the right-hand side, or vice versa, the right-hand side to look like the left-hand side. It is generally easier. Well, for this one, it doesn't really matter, but I can expand those exponent rules and then work backwards pretty easily, or I can get all of these to have bases of 2 and do that pretty easily as well. I'll show you both options just so you have the option to choose which one is easier for you. I'll do the left-hand side here, where I recognize that I'm adding 2 exponents, and that must have resulted from a multiplication of 2 bases, right? Because if I multiply 2 things that have the same base, I would just add the exponents to simplify that as 1 base. So I can use that rule in the opposite direction. I'm just going to use the commutative property of multiplication here to flip that around. 2 squared is 4 times 2 to the negative 3x. And notice, structurally, I'm halfway there, right? I've got that 4 out in front. I just need to somehow get that to look like 1/8 to the x. So I'm going to rewrite that a little bit differently as 2 to the negative 3 to the x. Because again, if I see a product of 2 exponents, I could rewrite it as something we raised to an exponent raised to another exponent. And the reason I would do that is because, lo and behold, we have a negative exponent, which means I could bump that down to the denominator and make it a positive exponent. But we all know what 2 cubed is. That's just 8. And I have hence satisfied this identity, proving that it works for all values of x, that just manipulating this with our properties of exponents, the left-hand side is always equal to the right-hand side for all integer values of x. I want to show you one more thing, though. What if instead I wanted to work on the right-hand side? You could, and I'd say for this particular problem, it's the same level of difficulty to do that. So I'm going to erase my work here. And I'm going to try to massage the right-hand side to get it to look like the left-hand side. So notice that on your left-hand side, you only have a base of 2. So I want to rewrite both of these things here as having a base of 2. Well, I know 4 can equivalently be written as 2 squared, and I know 1/8 is the same thing as 1/2 cubed. Now, if I'm dividing by 2 cubed, I could bring that up to the numerator and just make that 2 to the negative 3rd based on the properties of exponents. And I'm raising something to an exponent to another exponent, so I know equivalently I could multiply those exponents to make that 2 to the negative 3x. And again, if I'm multiplying 2 bases, I could add those 2 exponents to make that 2 plus negative 3x or minus 3x. But by the commutative property of addition, I could rewrite that as 2 to the negative 3x plus 2, which is precisely what I wanted to get that to look like. So either of those ways would work. Keep in mind, though, I'm not applying any properties of equality. I'm not multiplying both sides by something. I'm not adding something to both sides. I don't know that this is a true equation yet. I'm trying to verify that it is. So you want to stick to one side and try to massage that down to make it look like the other side.